Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a topic in mathematics that is measurement, but specifically we're going to deal with the concept of significant figures. Now we're going to discuss in a nutshell, of course, our objective, of course, trying to study this concept of significant figures, and we shall borrow some concepts or try to give a summary of what the term measurements and some of the relevant terms that are being used inside there are. So in that case, without further ado, I welcome you. Let's begin. So as I've said, we are going to study today about the concept in measurement, that is about significant figures. So in that case, of course, we shall look at what the term significance implies, and we're going to also to look at some of the specific terms which are used under the broader topic of measurement, which are going to assist us understand this concept of significant figures. So in that case, of course, we can literally say that the term significance means something that has got implication or relevance. So in that case, we are going to look at that one in as much as or insofar as numbers are concerned, and these numbers will be derived, as we have said, from the topic of measurement. So in that case, it's good for us to understand what the term measure means, because this is going to give us a basis for understanding significant figures. Now this term measurement simply means to compare in size or magnitude with a similar standard quantity that is called a unit. So measurement means to compare in size, or magnitude with a similar standard quantity that is normally referred to as a unit. So in that case, there are some terms which are being introduced in this case which are going to bear relevance. So in that case, the first term that we come across is to compare, which means there are two aspects which are being looked into. So to compare in size or magnitude with a similar, this one also is important for us, with a similar standard quantity that is known as a unit. So in that case, if we are trying to see this particular definition, the term similar means that you compare things that possess a similar attribute or which are in nature are the same. For instance, if I can compare the size of maybe like a cow, I'll get it with another cow maybe in terms of size, sex, etc. So in that case, if I compare a cow and I say I'm comparing it with a sheep, then there are some attributes which of course they are going to miss in this case. So this one confines us to the concept that we have to compare. Of course, this is just maybe something that I'm trying to compare. Of course, let's say talk about if I'm comparing like which kind of object can I say? Maybe the size of a metal. I'm going to compare it with another, of course, quantity. We can, or which, let's just use a relevant example. Let's say, for instance, sugar. If I want to know the size of two different sizes of sugar, I'm going to compare it with another one. Maybe I'm measuring something like weight. So in that case, one of them will be the ones that I'm going to use as a point of reference. In that, if I know the quantity or the measurement of this, and it's the one that I normally use to consider finding other quantities of sugar, then this one is what is being referred to as a standard quantity. So a quantity that you use to know the size or the magnitude of other quantities which are unknown is what we call a standard quantity. So in that case, from this definition, that is how we are going to compare the size, or just use the term the standard quantity. Now in this case, there are other standard quantities depending on what kind or measurement you are making for either liquids, gases, solids, lengths, etc. There are other standard quantities, of course, which we are going to look at. So now that we have seen that to measure is to compare with a magnitude or size with a similar quantity that we refer to as a unit, then there is a derivation of this particular term that we call measurement. Somebody says he has done is measuring, of course, is to measure to compare in size. Now the term measurement refers to the ratio of magnitude of any physical quantity to that of a standard. Now this is a measure whereby, which means is the ratio. This is the ratio of the magnitude of any physical quantity So measurement is the ratio of the magnitude of any physical quantity to that of a standard. Now that we have said that a standard is a quantity that is used as a reference point in order to determine the size or magnitude of other quantities, the term measurement refers to the ratio, or a measurement refers to a ratio of the magnitude of any physical quantity to that one of a standard. Now the process of making a measurement, of course, we are going to see further, is known as mensuration. So if we come across this term during our discussion, now the process of taking a measurement is referred to as mensuration. So that one being said and done, as I've mentioned that there are different units that we can use to measure different quantities depending on need and convenience. Of course, and these different units, they are normally accepted by a community of scientists, or maybe some bodies or a legal body of different jurisdictions. Can it be a country maybe, or a region, etc. And the choice of these standard units that we are talking about depends on convenience. As I've said, maybe tradition, the tradition of a particular maybe region, and even the existing laws of that particular region or land. So in that case, there are different units which are applicable. Of course, we are going to come across these ones maybe in chemistry, physics, and even in mathematics. So in that case, of course, we have talked about the term standard. And in any case, we are being asked now, what is a standard unit? I hope we will be in a position to define that now that we have said that it's a quantity that is used to measure or to compare with others. So, or we can just simply define it as a measure of a physical quantity with which other units are compared. So in this case, you'll find that the measurements that are being done using maybe different instruments that are at our disposal are not always perfect. For instance, if I have an instrument like a meter rule, maybe, or just a meter which is from 0 to 100, maybe this is centimeters, so 0 centimeters. So this one is defined as a meter. The stretch from this point, the magnitude or the size of this length, or this stretch from 0 to 100 centimeters, is defined as a meter. Now suppose I have just a bar, can be a metal, wooden bar, etc. that I'm supposed to measure. I just bring that starting point of a bar and make it coincide with the 0 mark, and then I see the extent to which this metal this metal bar stretches across. So in that case, maybe at this point, of course I've expanded these units, they are not in the ratio of proportion of this. Suppose this is from, okay, let's say at this point is 71 centimeters, and this is 72 centimeters. Suppose this length or this bar that I'm trying to take a measurement for reaches at this particular point, and then it is ending there. So for me to make a measurement from this, of course I know that from my estimation, this particular point is past half mark between 71 and 72. So I can say that the measurement with the certainty is that it is 71 centimeters. But there is a fraction, of course, a decimal fraction, which I'm not certain about, because due to the accuracy or maybe the range that this particular instrument can measure, it cannot be able to indicate for me at what point this one terminates. So I'm going to guess and say that this is at point around 0.5 or 6 there, or maybe I can say 0.6, 71.6 centimeters. But since I do not have the exact figure or accuracy for that, there will always be some inherent uncertainties, which we are of course going to call experimental errors. Experimental errors. Now, for us to ensure that this measurement, of course, is near accuracy, we are required to of course include those experimental errors in this particular measurement. So if the accuracy of this measurement, of course, this is 71, so I'm going to indicate that one as, okay, just so that one plus or minus 0.1 centimeters. So the reading for that one, we say that that one is a reading, experimental reading, of course, which include the uncertainty, which I've said that for us to make a measurement, we cannot be certain that the measurement that we have made is accurate, or it will always bear some kind of uncertainties. So in that case, this measurement will be 71.6 plus or minus 0.1 centimeters. Now this one caters for those uncertainties that we are talking about. So this one requires us, of course, to indicate numbers in significant figures. When we are doing a large calculation, maybe we might encounter a number that, or an answer that has got a very large decimal fraction. So that one will require us to include this concept of significant figures for us to make it simpler. So in that case, we are not going to look at these experimental errors for now, but those ones are going to appear later. So for us, we will just confine ourselves to these particular terms that we are trying to define. So in that case, from the measurements that we are making, the figures that we are going to get from this and other measurements are the ones that will require us to indicate or write those measurements in significant figures. So, and there are specific operations that are going to be done on those measurements, like addition, subtraction, division, and multiplication, of course, which are going to affect those significant figures, but we're going to look at that. So we shall look at another term that is known as, now that we have looked at measurement, accuracy, mensuration, measurement, how to measure measurement and mensuration. We've also looked at an example of how we can make a measurement. And let's look at this concept of accuracy. So in that case, as we have said, it is difficult for us to just measure the exact values of a quantity, or just exact value of a quantity without incurring some errors. So those errors are inherent in that they are always there, because we cannot measure something to its absolute certainty. So in that case, to get about those errors, I've said that we are going to write some degree of uncertainty which is going to indicate the accuracy of that measuring instrument. So this degree of agreement between the experimental values of a physical quantity and its corrective value defines what we call accuracy. So in actual sense, we can define accuracy as the degree of agreement, between an experimental value of a physical quantity and its true stroke corrective value. So as we have said that from the process of mensuration, it's very difficult for us to attain the true corrective value for that measurement. Of course, we are going to state that measurement in terms of accuracy, and those uncertainties that we are trying to indicate, plus or minus 0.1, was trying to include or try to give the measurement of a value some degree of accuracy in case there's maybe a slight error from the positive or the negative side. So I've just deliberately put this one in quotes because, as I've said, it's difficult for us to get the an absolute value from the measurements. So in that case, accuracy is the degree of agreement between this experimental value and the expected true value. So as I've said, of course, that one we're going to look at it in details. Just going to give this definition and its relevance in significant figures. And then we are going to look at another concept that is known as precision. Now, precision in a sense refers to the degree of consistency and reproducibility of a measurement. Now, this refers to, of course, as we said, accuracy is the degree of course, the degree of agreement between experimental value and the true value. Precision as well is a degree of consistency. This is the degree of consistency. The degree of consistency or reproducibility. Reproducibility of a measurement. So in that case, if we are talking about precision, if I take a measurement maybe of a bar that I talked about, maybe if it's coinciding with a 71 centimeter mark, or maybe 71 and a slight, of course, measurement ahead of there. If I do the first measurement and find it's 71.5, and then I do a second measurement 71.6, then a third trial 71.5, a fourth trial 71.5. I say that the 71.5 that has repeated itself 3 times is what I call consistency. So in this case, this kind of consistency is what we call precision. So I'm being precise in trying to take those kind of measurements. So in that case, we find that for different instruments, of course, we have different instruments, as I said, which are used to measure different quantities when we are doing measurements, like length, weight, volume, etc. So in that case, as we said, one cannot estimate the reading of an instrument better than its smallest subdivision. For instance, if I have a balance whose smallest subdivision, okay, subdivision means that, suppose this is So if this is maybe a meter rule that I'm having here, this is 1-2 centimeters. And from this point to this one, I can say that I have 10 subdivisions. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for that case, these subdivisions, I can say that it is, one of them is 1/10. So implying that one subdivision is 0.1 over centimeter. So this is 1 centimeter. Oh, of course, this reading is in centimeters. That is, of course, the units. Reading is in centimeters. Therefore, if it has 10 divisions, then one of those 10 divisions has got 0.1 centimeters. So I can say that the smallest subdivision here for this instrument is 0.1 centimeters. So in that case, I'm going to say that one cannot estimate the reading from this particular meter rule better than the smallest subdivision. So therefore, the maximum, or what we call the upper bound or a limit for this kind of an instrument, then it's going to be 0.1 times 0.1 centimeters, which is going to give us 0.01. So in case maybe I make a measurement from this particular point and then it terminates at that point, then I can say that it is 1 point. Of course, this is 1, 2, 3, 4, 5, 6, 7, 8. 1.8. And then the third figure, I do not have any uncertainty about it. And if it's maybe slightly above 2 or 3, and then I can say maybe it's around 5. So in that case, since I do not have the certainty for measuring that one, then I'm just going to indicate it, of course, to this number of figures. So in that case, that will be giving it the upper bound that we are talking about. So in this case, I've said that we're going to look at different kinds of errors or uncertainties that we have used. So in that case, to express this precision, we usually indicate the readings in significant figures. So that's why the concept of significant figures came from, in that there are some figures which are going to bear some kind of relevance in a reading, and others, of course, might have a very small or no relevance in that kind of a reading, or a very small impact in that reading. So let's look at the concept of significant figures and try to see what they are. So in that case, we said that significant figures so from a definition, significant figures refers to digits of a number these are all digits of a number that are used to express digits of a number that are used to express it to the required degree of accuracy. So these are all digits, or we can just write these are digits of a number that are used to express it to the required degree of accuracy. So this one we can add and starting from the first and 0 digit. There's a reason as to why we have added the last statement, of course, because of decimal fractions, which of course we need to be expressed in significant figures. So in actual sense, from the definition, these are the digits of a number that are used to express the required degree of accuracy. And now that we define the term accuracy, starting from the first non-zero digits, so I've said the last condition caters for those decimal fractions that we are going to say, which of course we're going to define in terms of significant numbers. So simply we can say that all non-zero digits are significant figures, and then we can say that also the zeros between non-zero digits also forms part of the significant numbers. So I'm referring to this one. For instance, I have a number 325.064 or 006. And then I have another one 0.00325. So in this case, what we were trying to refer to, that the non-zero digits of course are significant figures, and when the zeros come between the significant figures, then those zeros are going to bear relevancy. Of course, as you can see, this one is trying to depict the degree of accuracy, the one that we were talking about, the uncertainty. So in this case, when the first non-zero digits, which is 3 of course at that point, starts in that number, then we can say that the significance starts from this particular point. So the significance of this particular value starts at this point, and we can say that those are just 3 figures which we are seeing at that point, which are significant. So first, we say the importance of studying these significant figures is to show precision of the measurements or calculations in that case, and to show the amount of uncertainty in the reported value, of course, which is a measurement. And then lastly is to express the precision of a measuring tool. So in this case, that is the relevancy or the importance of this concept that we're talking about. So fast forward, we can just go to our main concept now that we have done some kind of concepts which are going to assist us. So let's look at this kind of a measurement. And which is put against a scale 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say that the upper reading, which is a number, of course, is a scale, and then this may be something like an object. We had shown something like this before. We did a demonstration of this one before. Now, suppose someone is asked to make a reading from that kind of object that is gauged against a scale. Now, in this case, we're going to make an estimation. Now, from 6, we do not know which number appears after 6, but in that case, of course, we can make an estimation and try to see which is the second figure. Of course, from the readings, we can say that the measurement is 6 centimeters, but there's a fraction there that we are not certain of. Of course, we can say that maybe this 0.5 reading is at that point, halfway between 6 and 7, then the reading can be 6.6, around 6 centimeters. But as we said, we are going to include uncertainty, of course, of positive minus 1, simply because we do not know. This is positive minus 0.1. Because we do not know about the second figure there, so it can either slightly be 6.7 or 6.5. That is why it's relevant for us to include that uncertainty. So this is how we're going to indicate the reading, 6.6 plus or minus 0.1, in order to cater for that uncertainty or the second figure that we do not exactly know what it is. So by doing that, we have indicated the uncertainty of that scale, and we have indicated the recorded value as it is required. So that is the first example. And then let's look at another one. We can have another example, of course, of this reading that is to 1 decimal place. So let's look at another one. Suppose I have maybe another object that is etched against a scale, which is of course now having a higher accuracy. And let's say that this scale just extends towards that side, and this is 10.7. Now the first one we looked at, it was just a whole number without a fraction, and the second one is bearing a fraction. So which means this instrument's precision is much higher than the first one that we were looking at. So in this case, we are going to make a reading. Now, as we can see, there is a 0 between the 3 digits. So in this case, we are going to say that this 0 is irrelevant. So these are already 1, 2, 3 figures that bear significance. So in this case, when we include the uncertainty, we can say if the halfway mark is around that place, then we can say that this is around 10.64, but we are not certain of the fourth figure there. So in this case, when the smallest reading of this particular instrument is 0.1, then the uncertainty for that one, of course, is going to be 0.1 times 0.1, which is 0.01. So in that case, we are going to include that one in this reading and say plus or minus 0.01 centimeters. This scale, of course, is in centimeters. It's good for us to indicate the units. So in that case, this is how we're going to make the measurement, catering for that degree of uncertainty. So in that case, this one we shall say that the reading has been made in 4 significant figures. And each and every one of those digits bears significance in that reading. So there are some specific rules for us as we go quickly forward. There are some specific rules that apply in indicating these significant figures, which of course we need to know. And it's a set of around 5 rules that we're going to discuss. So the first one, the first significant figure is the first digit other than 0 from the left. So from the left, maybe we write a number 29.84. And then in that case, maybe if it's a reading 29.84 liters, and then the first significant figure is the first non-zero digit from the left. This is the left, so the first non-zero digit is the first significant figure. So in this case, we are going to see that this is going to be applicable across, in that there's a number I'd written before and said that the first significant figure is the first non-zero digit from the left of that measurements reading. So that is condition number 1. So condition number 2. So condition number 2 is that, so the zeros from these particular digits that I was trying to demonstrate, 3 to 5, the zeros to the left of that non-zero digits are not significant. So therefore that number that I've written there consists of only 1, 2, 3 significant figures. So for numbers of this one and of a similar kind, we are going just to start counting significant figures from the first non-zero digits from the left. So that number consists of 3 significant figures. Now zeros between significant figures are also counted as significant figures. Suppose I had a number which of course is 1.0325, and this one that is appearing here, the first digit, that is a non-zero digit, and the other one contains zeros in between. So these zeros are going to be significant figures. So in this case, I'm going to count 1, 2, 3, 4, 5, 6. So this is 6 significant figures. So due to the fact that these numbers have made zeros to come in between non-zero digits, it makes them to be 6 significant figures. So condition number 3, of course, we have said that the zeros in between. Condition number 1, we said that the first and 0 digit from the left is the first significant figure, and then number 2 we say that the first and 0 digits, of course from a decimal fraction, is the one that starts to be counted as a significant figure. Number 3 we say the zeros in between 2 and 0 digits form a significant figure. Now for a measurement that is containing decimal fractions, like for instance 7.0 seconds, that one has 2 significant figures. So in that case, of course, this one indicates the precision of the measuring instrument. For instance, for this is 7.0 seconds, of course, that 0 that is appearing after 0.7 is going to be significant because it contains the precision of the measuring instrument. So in that respect, if I were to write 7.00 still seconds, this will give an implication of 3 significant figures, whereas this one is 2 significant figures. And as we have said, they bear a significance in a sense that they are taking the precision of a measuring instrument. So that is for measurements that contain decimal fractions. Now the number of significant figures, of course in units of measurement like centimeters, millimeters, meters or kilometers, of course is independent of the unit. So the number of significant figures is independent of the units. Now suppose I have a measurement, maybe the one that we have used for that instrument or for that distance, that is 10.6, and this one is indicated in centimeters. I can express this one in terms of millimeters, which is 106 millimeters. Still I can express this one in terms of meters, which is 0.106 meters, and which still can be expressed in terms of maybe kilometers, which is 0.0000106 kilometers. So the concept, the last concept that we are talking about is that the number of significant figures is independent of the units of measurement. So these units of measurement that we are trying to express here, the units of length, they bear no significance in the number of significant figures. If you look at the rules that we have discussed, of course, for the first case, this is 1, 2, 3 significant figures, 1, 2, 3 significant figures. This is 1, 2, 3. This is the first and 0 digits, 1, 2, 3 significant figures. The first and 0, 1, 2, 3 significant figures. So in that case, the effect of the measurement of the units which are being expressed here, they bear no relevance. So for that, they bear no or they have no effect on the significance of these figures. So in that case, that is going to be maintained to be 3 significant figures. So those rules that we have discussed are going to be applied across the divide for all the significant figures that we come across. Now, suppose we have some common operations that are going to be done on significant figures. How can the answers or the products or the results be expressed? The normal operations like addition, subtraction, division, and multiplication are also going to have some specific rules which are going to be maintained, of course, while dealing with these significant figures. Now, if we look at the first one, there's this concept of rounding off of some measurements. So in that case, the first digit to the right of the last significant figure, maybe if it is bigger than 5, it is rounded off. So in this case, we talked about inequality signs, or equality signs in that case, and we said that if we indicate using these figures, this implies that a number that is in front of 5 is bigger than 5, and this is smaller than 5. So in that case, if for the first condition, a number that is appearing, the first digit to the right of the last significant figure, maybe if I write 426 90.7. So in this case, we have said that the first digit to the right of the last significant figure. So in this case, because this is a non-zero digit, it's the last significant figure. So the first digit to the last of the non-zero significant figure, if it is more than 5, then we can round off this one and say it is 427. If it is less than 5, let's say for instance this was 4, and this 4 is dropped and we write 426. So if we were to express this one in a significant figure by trying to compare this last digit, of course, which is to the right, which is a non-zero, then we compare it whether it is either greater than 5 or less than 5, and that is going to give us a condition for either rounding it off or dropping it. For instance, if I say that the quantity of milk, let's try to see if the quantity of milk, for instance, is has been measured to this degree of accuracy. This is 42.54 milliliters, and we have been asked to express this one in 3 significant figures. Of course, if we try to look at these digits, first it is 1, 2, 3, 4 and 0 digits, which means it is already in 4 significant figures. But if we are asked to write it in 3 significant figures, then we are going to start counting from the left, first, second, third, and try to look at this condition, of course, that we have stated for this particular digit, and then that one will be expressed as 42.5 milliliters, bearing in mind that this number is less than 5. Therefore, as per this condition, we drop the number. And suppose, of course, it was 425.6. Then, as we said, this number is more than 5. Then we're going to round it off and then find that to 3 significant figures, this is 426 milliliters to 3 significant figures. So this is to 3 significant figures. So those are the conditions that we're going to use for rounding off. Now for addition and subtraction of significant figures, now there's a special case for addition and subtraction of significant figures, in that the answer will always be expressed to the precision of the least precise measurement. So in that case, let's look at maybe a measurement like 331.46 milliliters, and then we add, or it is increased by adding milk, more milk of 14.9 milliliters. If you look at these two particular numbers, of course there's a different degree of accuracy, and the level of significant figures, as we said before, this one is all non-zero digits, so it's 1, 2, 3, 4, 5. Already has 5 significant figures, and for the second one it's 1, 2, 3, 3 significant figures. So we have said that when measured values are added or subtracted, now they are rounded off to the precision of the least precise measurement, the least precise measurement. So in this case, if we compare 5 significant figures and 3 significant figures, this is the least precise measurement, implying that the addition of these two, the answer is going to be expressed considering the least precise measurement in that. So if we try to add this value, then we are going to get 331 point, that is 331 point, of course, so the first thing that we're going to do is going to express this number so that it matches the number of significant figures in that. So we consider that condition that we have already discussed for rounding off, and say that this one can be written as that 1.5 milliliters. So it has matched that one. This is to, of course, just a minute. So we have expressed it to the precision of the least, of course, the least precision measurement. So we add 14.9, and then we'll find the answer to be 346.4 milliliters. 1, 2, 3, 4. So to 4 significant figures. So in that case, that is the final measurement that we're going to get. And let's try to consider a second aspect of maybe whereby we measure the temperature. Suppose the temperature of maybe an object is 99.3 or 99.27 degrees, and then the temperature is increased by 22.5 degrees centigrade. We can already see that the least degree of precision is that one. So therefore, for this one, we are going to express it in the least degree of precision so that it matches with that one, and then we find the sum, the two, for us to determine the final temperature. So this one will be expressed as 99.3 degrees centigrade plus 22.5 degrees centigrade, and the final answer will be expressed as, so sorry for that, so that is 99.3 plus 22.5, so the final answer will be 121.8 degrees centigrade. So this one, 1, 2, 3, 4 significant figures. So in that case, the concept is, whenever we are doing an operation that is consisting of these two values that have different degree of precision, we express the answer, or maybe we do an operation using the least degree of precision, of course, which is 22.5. So therefore, that one requires us to convert this first, which has a higher degree of precision, to match the lower degree of precision before you find final result. So then what happens to the case of multiplication or division of numbers with significant figures? So for multiplication and division of numbers, in this case, the number of significant figures in the result will not be greater than the number of significant figures in the measurements with the fewest significant figures. So this rule seems to be applied across the divide, in a sense that it caters for the lowest precision measurement, or the figure in the measurement with the fewest significant figures. That's for the case of multiplication and division. Let's look at this example. For instance, suppose I have a piece of plate or metal here, which measures 13.2 centimeters length and maybe 4.8 centimeters width. So if I'm requested to find the area of this kind of a piece of plate, or maybe a wooden piece of maybe like a board, of course area is equals length times width, which is 13.2 times 4.8, and the answer in centimeters. So in that case, I'm going to do a multiplication for that and find that the answer is 63.36 centimeters square. So in that case, we have said that the number of significant figures in the result of this particular operation will not be greater than the number of significant figures in the measurement with the fewest significant figures. So the fewest significant figures. So if we look at this, the significant figures for the length and width are different, in a sense that the length has got 3 significant figures and the width has got 2 significant figures. So implying in that case that we shall consider the measurement with the least significant figures, which is the number of course, significant figures to which the answer will be expressed. So in this case, these are 2. So if we consider expressing this one in 2 significant figures, the number that is following the last non-zero digits for 2 significant figures from the left is less than 5. So the answer will be 63 centimeters square for that area in expressing it in the least significant figure. So in that case, that is the operation that we normally do with the multiplication. And for division, we are going to look at this example. Now for division, suppose we have a figure that is like 3.78 divided by 120.7. These are 2 decimal fractions that we're going to do a division. So we write 0.0, that is that 132. So the answer is given as that. So from this we have 1, 2, 3, 4 significant figures. This 0 is between and 0 digits, so it's significant. So since has 4 significant figures, these are 3 significant figures. So the answer is going to be expressed in the list, the number with the least significant figures, which is of course 1, 2, 3. So in that case, the answer will be 0.0313 in its respective units, maybe it in centimeters, etc. So if we are doing an operation with whole numbers, of course, those are non-zero digit or natural numbers which are non-zero digits. Of course, for multiplication or division of measurements by natural numbers, the number of significant figures is preserved. For example, we multiply a significant figure or a fraction, or just a number like 1.96 liters by a natural number like 2, then this one is going to give us 3.92 liters. 3.92. So it's going to preserve the number of significant figures, which of course still remains 3. Now this one applies to quantities whose relationship is fixed by definition. For example, if I say that 1 inch is equivalent to 2.400 centimeters. So in that case, or in that regard, a measure of a length of 4.3 centimeters in terms of inches, so I just put